as you probably know, most of the data around the world are unstructured. So for instance, in 6 years ago, Oracle estimates that 90% of the data was unstructured, and it represents 85% of the data produced by companies. So processing unstructured data is very important, especially textual data. So we need to develop methods for retrieve the good information, the correct information, and also to extract the information from the text. So my talk is more on the extraction of information from text. In biomedical domain is very important because there is an increased amount of data coming from the scientific literature. There is a digital library where you can see all the scientific papers on the domain, and in fact on the domains, because there is several ones, medical domains, pharmacological domains, and also epidemiological reports. Textual data in biomedical domain are also electronic health record in hospital. So when you go to the hospital, there is a electronic text which is produced can be discharge summaries, radiological reports, and also more and more there are documents which are produced by the patient or for the patient. It can be document explaining disease or give some advice for better health, for instance, and so on. And also some patient can, in some country, for instance, I don't know in Ukraine, but in France or in the US, there are laws who patients have to understand the discharge summaries. So we have to develop some method to translate in the same language information text from defined by or written by specialists to be understood by patients, who are not very specialists of the domain. And there is also textual data produced on the social media, which can be useful to analyze the behavior of the patient or to predict some disease, for instance. You probably know some application of Google to identify the flus in the, from Twitter's message, for instance. Just for an illustration, on the Medline portal, which is an internet website where you can find most of the scientific publication related to the medical domain, there is a constant increase of the citation. I forget to check today, but I think at the beginning of the year, there are about 25 millions of reference, so 25 millions of papers who can be accessed on this domain, or at least the abstract and the title. And here you have the curve of the citation added to Medline portal per year. So it increases everywhere, so it can be difficult to read or to find the good information for any scientific. So what is text mining? Is mainly the extraction of useful and non-trivial knowledge from text. Extraction of information, you have to extract the information according to the application and also from text. So from text, it means that it's from written language with different kind of problem that I will present. And you have also to collect and link the information. And this information can be used to feed database or to feed knowledge base with this information. And basically it can be also see like a first step before data mining. Just to make the difference between both, usually data mining can be defined as the method and the algorithm to explore structured data. The objective is to identify rules, to identify trends or behavior which are not visible by humans. Usually text mining is more the development of method or algorithm to explore unstructured data. The idea is to extract, to identify and characterize the information which is available on the text. Text on the biomedical domain will lead to different kind of application. So it can be the search and the finding of relevant information in the electronic health records. It can be useful also for the hospital information systems. It can be also to provide a synthetic view of the patient-related information for epidemiological research, for instance. Also, you can mix this information with information coming from scientific literature to increase the to store the information in database for different kind of statistics, for epidemiology, for also information system and in hospitals. And as I said previously, social media can be used for the epidemiologic analysis, but also to educate patients to the health, what we call therapeutical patient education. And we can also mine social media to identify adverse drug effect. That means when you take a drug, for instance, there is some expected effect, good or bad, but there is also new bad effect that can occur because the clinical tests are not good enough or not sufficient to identify all the adverse effects, because there is different parameters to take into account. So what kind of information we have to identify in the text? So first, semantic entities. But for instance, here, I don't see it's a drug, for instance, or here a procedure, also disorders. There is also a lot of semantic relation between the entities. So, for instance, here we can have a relation between the drug and the frequency of the use of the drug, with the dosage also. We also want to identify temporal information. So here, for instance, the frequency or the duration of the administration of the drug, of the period also, and different kind of numerical information. But there is also some modifier of this information that can be used to identify the polarity, the modality of the drug, of the presence, of the use or the not use of the drug. Because sometimes some doctor can say that you don't have to give or to take some drugs to the patient because he's allergic to some kind of drug, for instance. I will give some details later. So here, for instance, it's extract from electronic health record in French, but it can be also electronic health record in English or in Ukrainian, probably. So we need various resources, terminology, mostly, ontologies, some more and more open-linked data, but also some lexica, consumer health vocabularies, according to the application, and also description, semantic description of entities. And we need to define some NLP approach, and this approach can be rule-based. They are more or less, they can be defined like more or less sophisticated regular expression, sometimes more. It's quite sophisticated. And also, you can also use machine learning approach, which can be supervised, unsupervised, or semi-supervised. So my talk is mostly on role-based approach, but because I like to use such kind of approach in my research. But sometimes when the problems can be better achieved with the machine learning approach, I use some approach. And so usually because I'm in a research environment, we evaluate the results against independent reference data, and sometimes it can be difficult to have such data. So difficulties. There is a lot of difficulty when you work with textual data. I don't know if is there a lot of people working on textual data? Okay, so you probably know what I mean by textual data are noisy, they are sparse, they can be multilingual. That means that you can expect that some text contains only English words. In fact, it can also contain other words. Text processing can be time-consuming. It may require contextual information. You need to take into account terminological or semantic variation. I will give you some example in the next slide. Semantic ambiguities also. There is also unknown or new words or terms on the text. That means that you can have very important terminology, very important list of acronyms. You probably find new terms in your text. So that means also if you want to, if you consider text like a space model, there is text can be seen as there is a high or unpredictable number of dimensions in your space. So ambiguity. So this is the problem related to specific domains, at least. But there is also the problem related to natural language processing in general, or natural language in general. So there is different ambiguities at each level, at the lexicon. So for instance, spell can be a noun or verb, apple can be a company or just a fruit, and so on, even in Ukrainian. For instance, for the syntax, there is a lot of problem. So for instance, in this sentence, the patient can be with a stethoscope, or the doctor can examine the patient with a stethoscope, and so on. And the other can be give some more funny interpretations. There is also ambiguity at the semantic levels. At the semantic level, for instance, a red pencil, or he reached the bank. Bank can be where you put your money, or the bank, the river. It can be close to the river. And there is also what you cannot see in the text, the position of the stress that can leads to semantic ambiguity. And also at the pragmatic level, which means that you need a lot of contextual information, or sometimes the previous sentence, to identify that the chicken will be eat or will eat. And also, if you see this sentence, you don't know if she referred to Susan or to Margaret, and also her to refer to Margaret or Susan. And you can find also such ambiguity in text. It's more, especially in biomedical or EHR text. Usually it's an ironic sentence. Usually most of the doctor written this in the text. It's for telling that the patient is not very pleasant. There is also variation in the wording at the semantic level. So, for instance, here you have different sentences saying approximately the same thing. There is also metonymy, metaphor, spelling error. For instance, in French, appel, it's called. So, if you are, it's a right word in French, but it can be also a spelling error. And also, what you can find some problem on the what I find it on some Ukrainian text is a mix of Latin and Ukrainian characters, which is a problem because there is a different UTF-8 code. So E and I and E, O and O, P and R, Y and U, and so on and so on and so on. That will lead some problem with string matching because if you want to find some Ukrainian terms which is incorrectly, which is not correctly written, it will be a problem. So now the problem. No, I explain the problem. So I will give you some explanation of the approach we developed. First, for the recognition of medication, assertion, temporal information in electronic health records, and also for mining literature to identify risk factors. And I will finish by a work we did on Ukrainian text to acquire terms from text. So the first one is, so usually I work with different kind of colleagues, either from computer science, either from linguistics, either from medical domain also. So the first work is related to the data produced, textual data produced in hospitals. So electronic health record describe the hospitalization. You have a lot of information about the patient, the problems, the therapies, the tests who pass the patient, and some additional information related to this information, like assertion or temporary information. And the best way to record all the personal information about the patient is to write text, not to put everything in a database. But texts are written by practitioners. It is written in a hurry, with mistakes, with a little incorrect or poor syntax. And it may be difficult to use to extract information. So this work, in this work, we try to identify part of the information inside the text: medication name, written information, dosage, duration, frequency, mode of administration, and the reason of the prescription. So basically a disorder. And also we try to characterize this information according to the certainty or the uncertainty of the information, and also with temporal expression. So this is a result of different participation to the I2B2 challenge, which is organized by national, maybe not National Library of Medicine, but probably the National Institute of Health. Usually we have the data for 3 months. We develop our systems, and we have 3 days to test our system on new data we didn't see before. So if I would like to show you what kind of drug-related information we try to identify. We just try to identify for this drug this information, and that's it. But sometimes the drug can be also just an hyperonym, a more general term, or also an international non-proprietary name, which is more general. That can usually this one is more a brand name. So regarding the assertions, we identify different types of certainty, positive and negative certainty. So for instance, the patient suffers from abdominal pain, and from negative certainty, the patient denies suffering from abdominal pain. And also we identify assertion regarding the degree of certainty. Hypothesis, the patient is called to the hospital if he suffers from abdominal pain. Condition, with shrimps, the patient suffers from abdominal pain. And also possibility, it was thought that the patient might suffer from abdominal pain. This is true sentence coming from electronic health record. So now, example of text you can find. This one is quite easy to read, well written also. We can identify some drugs, some information, temporary information, assertion, probably disorder, and so on. And so also frequency, dosage, and mode of administration. But there is also some text like this, with a lot of acronyms. I don't know if maybe you can understand this one. Believe me, this is drugs. Several drugs. I think it's frequency. I don't remember what it is, and so on. So we have to deal with such kind of text when we work on this I2B2 data. So according to the different year, we have different type of text, different number of tests. So there is about 1,200 documents. We participate 3 years to the challenge. So what is interesting is this: in the 2009 there is only 17 manual documents which are annotated manually. So we don't have a reference to develop machine learning systems, which is important here because our system was quite good because we developed rule-based system. And for the other, there is a more annotated document in the training set, and here also. So we collect some terminologies for the medication names, usually Eric's name, but also a group of therapeutic class of a group of medication from the FDA website. We also identify some ambiguous medication name. So, for instance, red blood cells can be medication, but also laboratory data can be mentioned in the exam. We also use diagnosis and morphology axis of the SNOMED International to identify the medical problems. And also we develop medical related information, usually regular expression to identify frequency, dosage, administration, and so on. And also different kind of rules to identify reasons. For the assertion, we use a well-known resource which is NEGEX, and also we add some markers or some information which are specific to the medical domain. For instance, on assertion, also contextual information, usually the some words also, and section headings. So for instance, there is a section with the drugs for which the patient experiences allergies. There is also a section with a social history of the patient, of the family history of the patient, and so on. And this information is not related to the patient. So we, according to the challenge, we use different rules, CRF models, We also tune idle-time system, and we annotate the document. I will give you some information on this annotation in the next slide. And we also design some post-processing modules to disambiguate some negative context or to disambiguate some medication name. And also we improve the CRF-based model with automatically extracted terms. So this is a quite classical pipeline for annotating a document with linguistic information. We first by identifying the sentence, then the words, the post tag, the lemma also. We also identify some names entities and also terms with semantic types. So this information come from regular expression, from terminologies, and so on. And we develop internal disambiguation to correct this kind of thing. So also for the we use the idle-time system, which provides some resource to identify temporal expression in English, in French, now in a lot of language. And we tune the system with temporal expression which are specific to the biomedical and the clinical domain. So for instance, post-operative day number, bead, and so on. And also we have to compute the correct date or the correct hour in the text. So we use the admission date to compute the correct date or the correct hour. So for instance, if in the text we have 2 days later and the admission date is the 14th of June, then the 2 days later will be normalized as the 16th of June. And we have some problems with frequency, so we add some external normalization for this kind of problem. What I didn't show you here is that for sometimes there is ambiguity in the annotation, and we leave the ambiguities at this level, and on the post-processing module we try to remove the ambiguity. So for instance, iron can be made sometimes, can be also library data. So if it is in a section related to the medication, we consider that iron is a medication. If the section will be library data, in that case, we don't consider it like a medication. And also, like I said, we reject medication name when in the allergy section. Like since we expect that the terminology was not exhaustive, we also developed a guessing module to identify new drug name, also misspell drug name. And so we observe some semantic patterns like medication, followed by dosage, followed by the mode of administration, and then we recognize non-phrase with the term extractor, and we apply the pattern after filtering and so on, and we can identify this drug name which are not in the terminologies we have at the beginning. So now the results. So we have defined 3 runs. We have to define 3 runs. The first run with use the main problem we identified in our system was the identification of the reasons. So we first start by using all the information we have from the terminologies, and then in the second run we use all the terms coming from the terminology which are related to reason, but without the information about the reason. And then we apply reason marker to decide if the term is a reason or not in the text. And also in the third run, we use the guessing medication name module. So the system achieved better result with the second run. You have here the full result with on exact match and inexact match. Inexact match means that if we find, we provide some terms which are not a good one, but the term included is a good one. In that case, it's an exact match. And our system was interesting because there is an important increase on exact match for the precision when this kind of thing was not observed with other systems. As you can see, the result for medication, dosage, frequency, and mode of administration are quite good, and for duration and reason, it's quite low. It was the same thing for all the system. The recognition of duration is quite difficult, and also the recognition of the reason of the relation between the term referring to a reason and the patient can be difficult. Regarding the assertion task, so there is quite good result for the category absent and others, but it was quite difficult to identify condition assertion and also, I think, possibilities. The main problem is that there is few examples for condition and possibility, so it was quite difficult to evaluate the result of the training of the system on the training set. And also, we just define one run for the temporal expression, and we achieve quite good results. So to conclude on this point, we have a system with a F measure of about 0.8, and we can the whole system is achieve good result because we use markers, and also we probably need to include syntactic structure to identify some assertion. And it's, as you saw, it can be difficult to define some certainty degrees due to the few examples in the training set. So other future improvement can be on the direction extraction. We probably need to add some prepositional phrases. We also had to improve the medical problem identification with a specific reasoning model. For the assertion, we considered that we need to enrich our system with synonyms coming from WordNet, for instance, and to improve patterns by using syntactic dependency or integrating a semantic class. What time? 25 minutes. Okay. I will give you some idea on this second work because I want to show you the last work. I need time. So on this work, we mine papers coming from the Medline portal, and we so Medline is a bibliographical database, and we want to extract risk factors related to disease. So there is previous work on the identification of risk factors, but not from text. That here we try to read all the paper on the risk factors and to identify the risk factor related to disorders. So we use a bibliographical database, only title and abstract, and we select only the abstract and titles which contain the sequence risk factor or factor of risk, which leads to almost 200,000 citations, about 42 million of words. And we also use a mesh for having some information about the disorders. We annotated the citations with linguistic information in the same way I previously presented. And also, since we don't have a terminology for risk factors, this is our purpose, in fact, we use a term extractor to identify terms which can be referenced to risk factors. And then we identify the risk factors. So I will give you some idea of the term extraction, mainly because it's most of my research, in fact, more than text mining. I work a lot in terminology acquisition. So it's a rule-based system. Just for make the difference between term recognition and term extraction, usually term recognition is you recognize terms you already know, which are already in terminology. You discover nothing more, in fact. With term extraction, you try to discover terms which are in the text and which are not in terminology. This is the main purpose. And so we need to compute two things. The unithood, which is can be defined as the strength between the components of a term, when there is a different several words, and also the termhood, which can be defined as the strength of the relation between the term and the domain. So we developed several years ago a term extractor for French and English text. Usually term extraction use a shallow parsing. We don't try to parse all the sentence. We will focus on the part of the sentence which probably contains terms. So we focus on noun phrase, and we also parse the terms to identify if some components can be also terms. So it will lead to a term candidate decomposition in head and modifier, so the syntactic role of the component of the term. Which is interesting with the term extractor, but it is that we try to parse the noun phrase, and if we don't achieve to parse the noun phrase, we remove them. So we also add some statistical measure, classical ones, number of occurrence, C-value, and so on. This is a software which is developed in Perl and which is available on CPAN. And it will be easily tuned to domain. So for instance, it had been tuned for a biological domain, and we try to adapt to other language. So I have an ongoing work for Ukrainian, also for Arabic. So how it works? So term extraction with Yeti start with text, which are lemmatized and post-tagged, so here for instance, and then we will try to identify chunk, not with regular expression, but by consider that all the part of the text which cannot be part of terms are the frontiers. So for instance, we remove verbs, or in fact we consider that we can split the text according to verbs, adverb, punctuation, and so on. So finally we have such kind of thing, so different word or noun phrase. And then we parse the noun phrase to detect term candidates. And we use progressive parsing. We start by identifying term candidates which are described exactly by parsing patterns. For instance, here you have some kind of parsing patterns with the adjective is the modifier of the term and the noun is the head of the term. So for instance, you have two examples here. No extra grammar tomorrow can be parsed in such way. This is the first step. And then we reuse this already a parsed term to parse all the biggest noun phrase. So, for instance, primitive and extra grammar, and so on. There is no limit for such kind of thing. So we use no extra grammar tomorrow term, which are parsed like this. So we project the information on this syntactic information on the part of the full term, and then we do a temporary simplification. We fold the already parsed part of the term to obtain such kind of term, which is correct, at least linguistically. And then we can apply the same pattern or the to parse this term, and then we unfold the term to have the full term parsed. So and so on. It's a little bit more complicated than like this, but it's a general idea. So when we extract the terms and we parse the term, we obtain such kind of thing with syntactic information. I don't give you the syntactic information here, but believe me, there is a syntactic information. And then we try to rank the term according to different kind of statistical measure, like the frequency, the term length, the C-value, and so on. And terms can be ranked according to this one, if you need. And then you can put a threshold to limit the number of terms in the list. So we use such kind of terms for the risk factor identification. Now we, at the end of this step, we have terms which can be risk factors, and we use semantico-syntactic patterns to identify pathologies and related risk factor. So, for instance, a term risk factor, this term will be considered like a risk factor if there is a trigger as a risk factor 4, and this one will be considered as a pathology. And we also, as we can have the information about the disorder with the mesh indexation of the text, we use this information to identify if there is pathology or not. Also. So for instance, if we apply this pattern on such sentence, or this pattern, you can identify some relation between this disorder and this risk factor or this risk factor, and so on here. So we apply these three kinds of patterns to identify relation, but also to identify risk factor and pathology. And we use the mesh indexation of this abstract to related risk factors with disorder we know which are related to the abstract. So we define relation with risk factors and pathology, this one, pattern, and also by the combination of this pattern and this pattern. So that means that if we find in the abstract risk factor and some pathology, we consider there is a relation between both. So only 10,000 abstract provide such information. We find only 300 pairs risk factor pathology, and by combining risk factor and pathology, which occur in the same abstract or in the same sentence, we extract more pairs, 15,000 pairs. There is still 5,000, about 6,000 risk factors which are not associated with any pathology. And only if we use the mesh indexing, we only have 5,000 pathology associated to abstract. So we compare this information with this information, and in that case we have triplets with risk factor, pathology observed in the text, and pathology which come from the indexation. We evaluate the results according to the precision. We perform also a manual analysis, or 2 manual analyses, and we also compare the results with some relationship we can find in SNOMED city. These relations don't provide explicitly the information regarding the risk factors, but they provide some information which looks like risk factors. So we want to see if what we find from the text can be also coded in a different way in terminologies. The evaluation leads to we evaluate the quality and the exhaustiveness of the risk factor for pathology. So we select one pathology, which is coronary heart disease, and medical doctor check all the risk factors related to this disease, and we achieve a precision of 88%. You can have some information of some example of the risk factor for this coronary heart disease. And also we compare 20 pathologies with information relation coming from SNOMED city, and there is only 19 relations which are common between what we find in the text and what is already recorded in the terminology. I show you some approach to use semantico-syntactic patterns to extract relation between two kinds of semantic entity in text. In that case of the risk factor, we achieve quite good results. We create a dedicated resource for risk factors. And such kind of method can be used to extract new information and also to improve some text mining system by additional information coming from scientific literature. We need to improve this work by using other patterns or other triggers like predictor, precursor. In that case, we should also define machine learning methods to learn the patterns and so on. And we also have to specify the risk factors according to environmental condition, social condition, clinical condition, and so on. And to take also into account negative context and modalities, and so on. Okay, last part of the talk. We also, with one colleague, we try to work on Ukrainian text. Now there is a lot of automatic tools to process European language and Japanese according to the regarding to the specific domains. But for many languages, there are still few NLP tools, and we were not aware of automatic terminology extraction systems, which are what we're interested in, and we try to define such approach to extract information from Ukrainian text. And the idea is to have a reference and also to evaluate the tuning of the term extractor ET on such kind of reference. And it was also a challenge to apply the approach as a transfer method on terminology extraction. So we use, well, I will switch a little bit this, but the methodology is mainly based on the transfer approach. In fact, we chose to use this kind of approach because we were aware of some parallel bilingual text collection, and we want to use such kind of information to extract terminology from for Ukrainian. So in fact, we use parallel corpora. We build bilingual and trilingual terminologies by bilingual transfer principle. So the bilingual, the cross-lingual transfer principle rely on the hypothesis that we have a parallel and aligned corpora for two languages, L1 and L2. We have syntactic or semantic information, any information in fact, from the L1, and we try to transpose this annotation from L1 to L2. In that case, we expect to obtain the corresponding annotation on the L2 language. Such principle, such method is an efficient way to process bilingual text for a lower source language. It gives good results for different type of annotation, part of speech, semantic categories identification, and also to identify some acoustic or prosodic features. So it was a challenge to use it for terminology extraction. But there is drawbacks. First, the quality of the method will depend on the quality of the extracted information on the L1 text, and also on the quality of the alignment. And usually the alignment of text is based on a statistical method, and so it depends on the size of the corpora. So usually bigger is better. And on low resource language, we don't have a lot of parallel text or aligned text. So we try to bypass such drawback, and to do this, we use Ukrainian Wikipedia, which is a source of relevant terms, and we use the terms we find in Ukrainian Wikipedia to identify relation between Ukrainian and French and English terms. And this kind of information will be used to help the alignment at the world level on the corpora. And we use the Medline Plus corpora. Medline Plus corpus is a collection of specialized text which is dedicated to patients who give some information about disorders, about health behavior, and so on. And it provides text in English and the translation in different language. For instance, in Ukrainian, but it can be also in Vietnamese, in French, and so on. So we have a lot of information in that case, and quite enough parallel data. And we use this corpus to build the terminology. So from the Ukrainian Wikipedia, we don't use all Wikipedia. We just use the Infobox for after selecting the page which are related to the medicine. So we use only this information, in fact. And the parallel corpora, so as I said, it's a patient-oriented brochure in 3 languages for our problem. It's on different kind of medical topics. So it's written in English. It's translated in different language. So it's translated in French, in Ukrainian. There is different kind of version. So sometimes we have difficulty to align the text, but it can be done. So you have an example here of text in English and the alignment or the translation in Ukrainian. So finally, we have almost 43,000 words for each language, which is quite enough to start a work for terminology building. So the first part of the work was to process the Infobox. So we just identify the Infobox in the Wikipedia pages, and we try just to identify the mesh code in the Infobox. And when we have the mesh code, we have win, because mesh is inside UMLS. UMLS, it's a collection of terminology in different kind of language. All terms in UMLS as a code is terminology are interrelated. So if we have the code, the mesh code for Ukrainian, we have easily the term in English and also the term in French. So in that case, we have easily relation between Ukrainian terms and French or English terms. So there is no natural language processing at this step, but this information will be used for the alignment. And here we also have synonyms. So for instance, DID2, it's a synonym of diabète avec insulinorésistance, which is related to the Ukrainian term. Now the transfer methods. So we observe 2 things. There is a lot of lists. So in that case, we define a first transfer method. We take advantage of the list. So if we identify, or if we extract a term on the English text, which is exactly an item of the list, we expect that the term in Ukrainian is related. It's the same. Oh, we expect that. No, I start again. We extract the term from the list. If the term is exactly the item of the list, since we have an alignment with the word on the list item in Ukrainian, we consider that the item list in Ukrainian is also a term. I think it's better in that way. And the second method, it's more difficult to use, but it's quite the same. We align the text between English and Ukrainian and French and Ukrainian. We extract terms and we use alignment to identify terms in Ukrainian after extracting terms from English or French text. So just to give you details of the methods, so we start with the mainline plus corpora with two pairs, the Ukrainian and French text or the Ukrainian and English text. We have clean and manually aligned text at the paragraph level. It's quite easy, not take a lot of time. Texts are have been downloaded in PDF, and we convert PDF in text. There is some program to help the cleaning, and we finish manually. Sorry. We post tag the text, the French and the English text with a parser. So for instance, for English it's a tree-tagger, for French it's tree-tagger and phlegm, which is a morphological analyzer for French. And then we extract terms with Yeti. And in that case, for the first transfer, we make the correspondence between the line in French and English, and then we obtain pair of candidate terms between English and French and English and in Ukrainian. No, Ukrainian and French, Ukrainian and English. For the second method, we use Giza++ suite, and we take advantage of this information to help the alignment, and also the Wikipedia pair of medical terms to help also the alignment, to improve the alignment. Because we don't have a lot of data, so all the information which is certain is useful. So now the evaluation. So we the extracted terms have been performed by a Ukrainian native speaker, which are good knowledge in medical informatics. Extracted terms are manually checked according to they are correct or not, and we also validate the relation between the French text term and the Ukrainian terms, or the English terms and the Ukrainian terms. And we just compute a precision of the results, since we don't have a reference to compute the recall on such data. And we also compute exact and inexact match precision. So in exact match, we consider that if the correct terms is included or include the candidate, it's correct. So for the bilingual terminology from Wikipedia, we just extract 357 Ukrainian medical terms. 1/3 is a single word terms, and we use mesh codes, and it gives 1,400 French terms and 3,600 English terms. So the number of the difference is due to the synonyms in the mesh, English mesh or the French mesh. So we obtain 1,500 Ukrainian French term pairs, and also 3,700 Ukrainian English term pairs. So here the precision was equal to 1 because the collecting method, in fact, we are sure that the terms are correct because we use only the mesh code. So it's not very surprising, in fact. It's not surprising at all. So for the first method of transfer, we obtain 400 Ukrainian terms with very high precision, which is expected. and the Ukrainian terms were associated with 300 French terms and almost the same number of English terms. So we can compute, we can obtain almost 300 trappers of Ukrainian, French, and English terms with a quite high precision also, and so on. So we can get some we observe that some relation involve synonyms. So, for instance, phthoma with 2 synonyms in English. Also, we observe that there is some several case forms with the same English or French form. There is few errors. Mainly it's due to a partial match between the 2 languages. For instance, sleep, dormir, manger, spate. There is also silence due to the variation in the translation. For instance, the word in Ukrainian is soin in French, but in English is your care. So we can make the relation between the Ukrainian term and the French term, but not with the English term. This problem will be solved by the second transfer method. And the other cause of silence is due to the error in the post-tagging and term extraction strategy. And the case when the term extractor miss to recognize terms, or in English or French terms. For the second transfer method, we obtain 9,000 Ukrainian extracted terms, but the precision is lower, only 0.45. There is a higher precision for the French and the English terms, but a lower number of terms for French and English terms. We assume that it is due to the rich morphology of the Ukrainian language. So we have different kind of form for Napan, Napadu, and so on. We also extract some synonymous terms. And also, yeah, some Udaru or Betia. And also, regarding the relation, we extract about 3,700 pairs of Ukrainian and French terms, and more for Ukrainian English terms. And if we consider separates, there is 4,500 trappers of Ukrainian, French, and English terms, with a precision of 41%. In exact match, there is an increase for the Ukrainian, a high increase for the Ukrainian terms, and a lower for the French English terms. We think it's due to the alignment quality. So regarding the error analysis, most of the errors are due, in fact, to the alignment. And we observe that if the alignment is correct, the Ukrainian terms are correct also by the transfer. We observe some interesting thing. There is most of the extracted terms are specific to the medical domain. There you have some example here. There is also terms which are close or approximating notion, or general notion. In fact, it's not surprising because it's patient-related document. So there is some patient-related terms. So it's terms which are general but related to the medical domain. And we also observe that there is terms, English or French terms, which correspond to phrases in Ukrainian. So, for instance, for undercooked or for indolor and so on. So, which is also interesting here, is that the transfer methods will be also useful to identify paraphrases in the same language, in fact. Or we can also have paraphrases of Ukrainian terms in that way. So to conclude on this last work, so we propose the transfer method for extract term candidate in Ukrainian, but also to develop bilingual and trilingual terminology. The results are quite good, and we demonstrate that the method is suitable to build terminology in a low-resource language. So there is future work. First, we can change the aligner, word aligner, by using a fast align. But we would like also to use statistical or morphological cues to improve the transfer approach. And we are planning to, we are working on the key phrase extraction from a scientific paper with the Institute of Cybernetics from Kiev. What is also the main problem here is that we need a parallel corpora. So what is will be, it can be difficult to have such data. So we would like to try to develop such approach with comparable corpora, which is the biggest challenge. So to conclude on this presentation, so as you can see now, if you didn't know before, text mining, biomedical text mining approach is a complex task which involves different types of information to link together. There is no specific strategy for identifying the information. You have to mix different kinds of strategies. You have to use a lot of terminological or linguistic resources, which can be more or less available according to the language. So you have to develop some method for some language. And the current challenge is the concept still the concept recognition, the disambiguation of entities, semantic entities, the normalization also, the development of multilingual approach, an approach for low resource language, and also the use of information on social media, because you have to make the link between the terms in social media, in what you write on Twitter, on Facebook, on any online discussion fora, is not the term you will find in terminology, because there is a lot of misspell, a lot of acronym, abbreviation, and so on. But this is a good and this is a useful information. So it is still a challenge on such data. It's mining the literature and to use open linked data. So it's a project which is funded by the French National Agency. And in that project, we try to collect from the literature interaction between drugs and food. Because sometimes, for instance, grapefruit can lead to adverse effect with some drugs, because some drugs contain this enzyme, and it will inhibit the enzyme, so it will be dangerous for the patient who take the drug. So there is information on the scientific literature, but there is not a lot of information in the database. So we try to mine the scientific literature for this, and we also use other databases which contain some information, and mainly from open link data, from open data repository like Drug Bank, CIDR, and so on. So this is a project we start at the beginning of the year. So to come back on this slide, from this drug, we try to just work on this relation and this relation. So we make the link between drugs, disease, and food. We also, as I said previously, keep on going the work on the transfer method and the term extraction from Ukrainian. And we are tuning term extractor Yeti for Ukrainian. And our other purpose is to develop approach for identifying semantic relation between terms in Ukrainian text. I think, yeah,
okay,
finish. Thank you. Dziękuję.